I've grouped the alkene reactions based on mechanism, and so the first two that we're going to look at, acid-catalyzed hydration and addition of HX, follow essentially the same mechanism. And there's something called Markovnikov's rule that can sometimes apply during this mechanism. As I mentioned, these two reactions have the same mechanism. The first is going to be acid-catalyzed hydration, which is just the opposite of dehydration. This time you're adding water across the double bond. The second is going to be the addition of HX across the double bond. This is called hydrohalogenation, which is the opposite of dehydrohalogenation that you learned in Chapter 7. And this time you're adding HX across the double bond. The first step of both of these reactions is going to be the pi electrons of the alkene attacking some acidic proton. So you get protonation on one side of the alkene, and the other side is left as a carbocation. The second step of both of these reactions is going to be the attack of some nucleophile to that carbocation, and in the end we're going to get an addition product. First, let's take a look at the acid-catalyzed hydration, and this functional group transformation is alkene to alcohol. So here's the protonation step. This is done in the presence of either tosic acid or sulfuric acid, and the pi electrons are attacking the proton. One side is protonated, the other side is left as a carbocation. In the second step, water is the nucleophile that can come in and attack, and it could attack from either side since this is a trigonal planar carbon. So you have to consider that when there's stereochemistry involved. There's not in this case. You initially will end up with the protonated oxygen, and then that's going to get deprotonated by a second mole of water to give the final neutral alcohol product. Two additional quick notes about this mechanism. One is that H2O is acting as the nucleophile this time. So remember when we talked about dehydration, we talked about the fact that the steps were highly reversible and that you needed to be able to drive the reaction forward by removing water as it was formed. With the hydration, this time the water's a reactant, and so you actually want to use excess water. Usually it's going to be the solvent, so that way you will keep the equilibrium shifted way to the right. The other thing is that H3O is generated in the final step, that final deprotonation where the proton would come off of here. And so we can say for that reason that this is an acid-catalyzed reaction, because at the end of each cycle, the acid is regenerated. Next, let's look at the addition of HX across the double bond. This is going to be the alkene to alkyl halide functional group transformation. The first step, once again, is protonation, but this time we have X- as a byproduct, which recall is nucleophilic. The X- is then going to come in and attack the trigonal planar carbocation, and the product is going to be an alkyl halide. Let's talk about the regiochemistry of the reaction, and we'll first look at just ethene, which is the alkene that we've been working with so far in these mechanisms. And the first step is the protonation. And notice that the proton can either go to the left or the right carbon, and that would leave behind a carbocation either on the right or the left carbon. And in this particular case, it doesn't matter because these are identical. But now let's see what happens when you have a substituted alkene. And so we can either get the proton on the left or the right, and that's going to leave behind a carbocation here or here. And this time these are not the same. The process that protonates on the left is going to leave a primary carbocation on the right. The process that protonates on the right is going to leave a secondary carbocation on the left. And the secondary carbocation is going to be the preferred pathway for this reaction. So during this process, you will not get the formation of the primary carbocation. You will get the formation of the secondary, which means the proton is going to the less substituted side, And this is called Markovnikov's rule. One way of sort of paraphrasing Markovnikov's rule is that when the first step of an addition to an alkene will generate a carbocation, the carbocation will form on the more substituted side of the alkene. There are different ways of phrasing this rule, but this is looking at it from the perspective of carbocation formation. Here's an example using HX. Notice that the protonation is going to take place on the right so that the secondary carbocation is formed, and then the halide ion can come in attack either side of this carbocation here to give the alkyl halide product. In terms of stereochemistry, let's take a look at when we're going to get some chiral centers out of this process. So, of course, the first step of the mechanism is the protonation step, and we have a side with one R group versus a side with two R groups, so the proton is going to end up on the less substituted side. By doing this, the carbocation is now on the more substituted side. And now the water, acting as a nucleophile, can come in and attack from either side of the carbocation. So notice there are two R groups here and then a different R group here. So you have three different groups on the carbon. So when the water comes in, this is going to make that carbon chiral. And so there's going to be two possible outcomes. You can either get this stereochemistry, or you can get it's enantiomer here. And here are the two products after the final proton removal. The same stereochemistry would hold for the HX addition, and so after the carbocation formation, of course following Markovnikov's rule on the more substituted side, the X- nucleophile could come in from either side of the carbocation, and you end up getting the two different stereoisomers, the enantiomers.